Pues continuamos con el curso y el día de hoy tenemos un invitado como es lo normal al inicio. Él es Hugo Flores. Se nos une el día de hoy directo desde la ciudad de Chicago, donde está haciendo su doctorado en la Universidad de Northwestern. Hugo tiene experiencia claro, en el deep learning de audio y de señales de series de tiempo, pero él más específicamente ha hecho trabajo que nos va a hablar un poco sobre cómo usar estas técnicas como plugins de Audacity y también trabajo de few shot learning para poder generar modelos que tengan capacidad de aprender con pocos ejemplos. En el caso pues de instrumentos musicales. Entonces, Hugo, estamos muy contentos de tenerte aquí y es un verdadero honor que hayas aceptado la invitación. Entonces, sin más que decir, te paso el micrófono. Gracias.
Muchas gracias, Irán. Mucho gusto a todos. Aquí voy a compartir la pantalla. A ver, cool. ¿Pueden ver mi pantalla? Perfecto. Um, entonces, creo que la charla la voy a dar en inglés porque un montón de esos conceptos los manejo solamente en inglés. Intenté traducir de español, no me fue muy bien, entonces vamos a tener que hacerlo en inglés. Pero sí, a ver, context switch. So, hello everybody. I'm Hugo Flores Garcia. As Iran said, I'm getting my PhD at Northwestern at the Interactive Audio Lab. Um, so, to start a little bit about me, I was born and raised in Honduras. I moved to the US when I was 17 to get a degree in electrical engineering. I graduated in 2016 from Georgia Southern University, and now I'm getting my PhD in computer science at Northwestern University, which I'll hopefully finish in 2025. Hopefully. I'm also a jazz guitarist. I love my cat. And I love to make interfaces for making music, whether that involves deep learning or not. I just love to find ways to connect technology and music together in general. Another cat picture, coding, just for content. Cool. And I'm going to start by talking about this paper that we published, I think it was last year, on leveraging hierarchical structures or inherent hierarchies in musical instruments so that deep learning models are better at recognizing these instruments, especially a wide variety of instruments. This work was done with Aldo Aguilar, Ethan Manilo, and Brian Pardo, which are also all at Northwestern University. It's worth noting that this paper won the Best Paper Award at ISMIR 2021, so yay. So a little bit about what musical instrument recognition is. Musical instrument recognition is the task of locating musical instruments in an audio recording. So the idea is that we have this sort of piece of audio and we don't know what's in it. We know that it's musical instruments maybe. And our job is to find out what musical instruments are present and when in time do these musical instruments happen. This kind of some applications of musical instrument recognition would be mostly really useful in digital audio workstations like Logic, Pro Tools, etc. They could help organize really large sample libraries, automatically group multiple tracks or organize tracks when you're working on like audio projects with lots and lots of instruments, and also aid in the navigation of long tracks by content. One of the motivations for this project was actually for designing a musical instrument recognition system so that people who are blind or have visual impairments, they don't have access to the visual waveform that we have to sort of like, identify when things are happening. So part of the motivation behind this project was the ability to sort of label and design interactions inside of the audio editing environment so that people can sort of jump to the next saxophone in the track without having to scan or listen to the entire thing. So uh, these systems for musical instrument recognition, even though we have been working on them for more than a couple of years, they're still not available in digital audio workstations. They're not available in Pro Tools or Logic or anything like that. And one of the main issues is that most of the musical instrument recognition models that you see, they can only handle like the same 10 instruments or the same 7 instruments. And just to really make an example out of this, this is one of the this is Metley Solos. It's one of the prominent data sets that we use to train on musical instruments. And if you look at it, the list of instruments that it's capable or that it's included in this data set is just these like same 7 instruments that you see in a lot of Western music, but it also leaves a lot of other instruments and a lot of cultures behind. So this is sort of the problem that we're trying to aim at. And to compound the problem, we also don't have enough training data. We don't have enough data for all of these instrument varieties that we want to be able to label. And collecting more data for all of these instruments isn't really feasible. It's like it would be a really, really long process, and there's always going to be unanticipated musical instruments that we would like to label. There's always going to be or not even like new musical instruments to label, but also different granularities to which a person would like to label. So maybe a person would like not only to discern between a guitar and a bass, but maybe they would also like to discern between different types of guitar, maybe a nylon string guitar and electric guitar. And maybe they want to discern between different types of electric guitars. So maybe they want to differentiate between a Fender Stratocaster and a Gibson Les Paul. And we're sort of trying to build a framework to be able to do this sort of stuff. Something that we're going to take advantage of is musical instrument hierarchies, because musicologists will categorize musical instruments within different hierarchical frameworks. Like one of them is sound production mechanism. So we can sort of organize instruments hierarchically depending on how they produce sound. And we can take advantage of this musical instrument hierarchy by learning an embedding space, a feature space, a latent space that is meaningful for new classes that the model or the neural net has never seen before, but it has seen instruments that are related that via the hierarchy. So for example, maybe we have never seen, our model has never seen a Puerto Rican cuatro, which is a string instrument with like 8 strings, and each pair of strings is like an octave apart, and a guitar. And we have lots of data for the guitar, and we have little to no data about the cuatro, but maybe we can build a model that sort of learns that the cuatro and the guitar are sort of related, and we can sort of take advantage of this during training to learn new instruments on the fly during evaluation or in the real world. So how we learn new instruments on the fly or after training is using few-shot learning techniques. And so in a few-shot learning setup, the user or whoever's using the model in real life would provide a support set of labeled examples. And a set of query examples that we'd like to label. So there's the support set. These are like the examples that the user provides. So maybe I want to differentiate. I'm the user, and I want to differentiate between a guitar, a Puerto Rican cuatro, a flute, and a drum. And maybe the model has seen some of these instruments before. Maybe it hasn't. But I'm going to provide it with some examples of what each instrument sound like. And the idea is that we're going to do this with few shots. So we're only going to give it maybe 10 examples per instrument, which is sort of like a feasible amount of data that a user can compile by themselves. And the idea is that if we use this kind of technique, we're going to be able to learn new instruments with around 10,000 times or 1,000 times less data to learn a new instrument. So if you're doing regular supervised learning, you're going to need sort of like 10,000 examples on the order of that, maybe more. And if you're doing few-shot learning for new, rare classes, you're going to use orders of magnitude less data. So our work builds on prototypical networks, which is like a specific type of few-shot learning. In this sort of environment, we have these green dots here, for example, are the support examples. So maybe all these green dots are guitar examples that the user provided, and all these blue dots are maybe the flute examples, and these are maybe the drum examples. And prototypical networks will compute a prototype, which is sort of like one embedding point to describe the entirety of a class. So I have one point here to describe all of the guitars. And the way you compute this is by just taking the average of all the examples. So I'm going to grab all the guitar examples, and I'm going to take the mean or the average, and that's going to be my prototype for the guitars. And we grab one prototype for all of the instruments that we want to label. And then whenever you have an unlabeled point, something new that you haven't seen before, you just calculate the distance to each of the prototypes, and then you label it with the closest prototype. So in this case, this orange prototype was the closest one to this point, so this is probably an orange dot, or a drum, as we said before. So like I said, the prototype is computed using the mean vector of the support examples, and we're going to predict the class with the closest prototype. The problem with this method of prototypical networks is that it doesn't incorporate the hierarchy that we wanted to incorporate earlier. So what we do to sort of like extend upon this is we incorporate a hierarchical label structure into the embedding space. We sort of like build this, we build an embedding space to sort of mirror the musical instrument hierarchy that we have. And we do this by doing the prototypical network like aggregation, computing prototypes for the fine-grained set of classes. So maybe you have guitar, and then you have violin, and you make a prototype for a guitar, and then you make a prototype for a violin, and then you average the prototype of the guitar and the prototype of the violin to make a prototype for just string instruments in general. And you keep doing that up and up every time you go up a level, and that way you're taking advantage of the hierarchical relationship between a guitar and a violin, and sort of like learning that into the embedding space. To give sort of like a more detailed example, here the user provides 4 examples for a saxophone. The red dot is a saxophone, 3 examples for the bagpipes, and then 3 examples for the clarinet here. This point in the center is the prototype for the saxophone, the prototype for the bagpipes, and the prototype for the clarinet. And if we wanted a prototype for reed instruments in general, so clarinets, oboes, and so on and so forth, we would take the prototype of the saxophone, clarinet, and bagpipes and take the average, make a prototype of the prototypes to get that representation. And we do that similarly for all the brass instruments, and now you sort of have like 2 levels. So you have the fine-grained prototypes, and then you have the coarse-grained prototypes. And you can keep doing this for as many levels as you want, or as many levels you have data for, right? And in terms of training and gradient descent and so on, we treat these as separate classification tasks. So the bottom is one classification task that's going to use multi-class cross-entropy, and the task on top will be treated as a separate task as well. So this is kind of like a multitask learning scenario where you're optimizing for different tasks at the same time. To sort of aggregate these classification types, tasks at different levels of the hierarchy, so we need to sort of like summarize these tasks into sort of one loss value that we can then do gradient descent on. We do this by adding them together with a exponentially weighted loss. And what we do is that we place the most weight on the bottom level of classes, because that's really what we care about. This is what the user sees. The user wants to label a new instrument, and that instrument is usually going to be placed on the lowest level. And then we place exponentially less weight as we go up the hierarchy, which is the reason we're doing this, and then I'll show this in the when I talk a little bit about the experiments that we did, is that we need to prioritize this task because this is the task that we really care about. We're only using these higher level hierarchical tasks to learn an embedding space that's going to have these hierarchical relationships into account. So I'm going to talk a little bit about the experiments that we did. So we evaluated our proposed prototypical network in a few-shot learning task composed of instruments that we had never